we know that a dielectric is an insulating material that can be polarized. And if we think about it, a polarized dielectric is going to have dipoles throughout the material. So let's take a look at a polarized dielectric. So in green, just going to draw some shape of my material. And there's going to be multiple dipoles throughout the material. Let's make these bigger. So then all of these would just have negative charges on one side and positive charges on the other side. So we kind of get the picture here. You also have an applied external electric field, so we draw that too. So having these different dipoles and dipole moments throughout the material, it's going to give rise to different electric fields and potential at different parts of the material. So we have to be able to characterize the different polarized states of a dielectric. So we use a polarization vector P to characterize the polarized states of a dielectric material. So let's first take a look at how we can do that. So at a particular point within the material, your polarization vector can be determined by constructing a small volume delta V around the point. So let's ask us, how we construct small volume delta V around a point in the dielectric, and then we're going to add vectorially all the dipole moments Pi within that small volume. So you end up with P is equal to the limit as delta V approaches 0, because we want to be able to minimize this little volume, and we are going to get the vectorial summation of all the dipole moments. And you'll know from before that a dipole moment can be calculated by multiplying a charge times d. So let's try and determine a couple of the things here. So just put a quick note. So when we take a look at this equation, we have the limit as delta V approaches 0 of the summation of the dipole moments divided by delta V. And the summation is going to be from 0 to n times delta V. So we want to define n as the number of atoms per unit of volume. Every dipole moment is defined by charge Q times D, where D is the distance or direction vector from negative Q to positive Q within a dipole. So now we've defined our polarization vector, and that gives us the ability to characterize the dielectric's polarized state. However, one of the most important things that we want to know, especially when we're solving problems, is how to calculate the charge densities throughout the material. So by being able to calculate the charge densities, we'll be able to figure out electric field, potential, and so many other things. So let's ask ourselves, let's do it here. What are the bound charge densities? And I say bound because we're looking at a dielectric, an insulating material with tightly bound electrons to the atom. So let's go back to this diagram over here. There's going to be two different types of bound charge densities. If we take a look, this material has a left side and a right side. So on the left side, there's going to be a surface, and there's going to be a surface charge there. On the right side, we can trace out the surface as well, and there's going to be a surface charge density here too. So that means we have, let's see how to best do this. We have induced surface charge, on both sides, and then from here to here on the inside you have what's called the induced volume charge. So how do we figure out both these charges? I won't go into the details of deriving these. You can take a look at the reference in the notes to get an in-depth understanding of how these equations were derived. But for surface charge, it's defined as rho s is equal to the polarization vector dotted with n hat. So what does this even mean? So apart from allowing us to calculate the charge density induced on surfaces, what this tells us is we just need to know the strength of P, the polarization vector, because this is a dot product, in order to determine the surface charge. So let's just highlight this. It's one of the important equations. Next, we want to figure out the volume charge. So the volume charge is going to be rho v is equal to negative del dotted with P. So thinking about this, let's ask ourselves what this even means. First of all, I want to talk about something called divergence. So as an aside, the divergence of a vector field such as P, at a point is the net outward flux of P per unit volume as the point tends to 0. So divergence is commonly used in calculating flow, especially for fluid dynamics. And so it's defined as, let's use P as an example. The divergence of P is equal to the limit as delta V approaches 0 of the closed surface integral P ds divided by delta V. And then you have the divergence of P being equal to del dotted with P, which gives you a partial derivative equation. So with this, we can now take a look at our volume charge density. It's defined as the negative divergence of the polarization vector. So what this means is the spatial rate of change of P determines the volume bound induced charge density. So there we have it. We have two equations that allow us to calculate the surface charge and the induced volume charge of a dielectric. These will come in very handy for future examples that we take a look at.